Okay, well, welcome everybody to the 10th SoFiE Seminar. I'm Andrew Patton, and I'm very happy today to be hosting a special edition of the Society for Financial Econometrics Seminar Series. Today we're having presentations from four job market candidates working in topics broadly related to financial econometrics. Our four speakers today will be Jean-Luc Denard from University of Zurich, Philippe Goulet-Coulomb from University of Pennsylvania, Ha-Yoon Zheng from New York University, and Merrick from University of Cambridge. I think the four topics are all very different and all very interesting. I think it's going to be a great portfolio of presentations today. Our fourth speaker today is Merrick from the University of Cambridge. Merrick will do the same format as before. You have about 17 minutes to present and then some time for questions. So if you'd like to unmute and share your screen, you can begin.
All right. Okay. Thank you, Andrew, for the introduction. It's a great pleasure to be here to present my work. This is a joint work with Professor Oliver Linton. We are both from the University of Cambridge. And in this paper, we focus on a broad class of models that are widely used in finance and economics, where the observed price is decomposed into an efficient price and an additional term which call it microstructure noise to reflect the various microstructure effects. So for the efficient price, we have a solid theory which implies it should be a semi-martingale. However, for the microstructure noise, it could have very rich dynamics depending on which market phenomena the model aims to capture. In this paper, we try to introduce a flexible way to measure the microstructure noise, taking into account the rich dynamics embedded in this term. And the estimation is not entirely trivial in the sense that both X and both the efficient price and microstructure noise are not observable. Only we were going to estimate the moments of noise using the observed price only. The measurement of microstructure noise is well motivated. If the market is perfect, if the market is efficient, the observed price should be identical to the efficient price in the sense that microstructure noise will be identically zero. Therefore, the dispersion and the persistency of the microstructure noise provide natural measures of market quality. We build on a general framework introduced recently in a seminal work by Jacod and Zheng, where the efficient price could have stochastic volatility and jumps. Microstructure noise could be serially dependent, endogenous, and non-stationary. And the framework also allows for a general random observation scheme. Based on this general framework, we introduce a non-parametric method to separate separate the microstructure noise from the efficient price using the observed price only. We will demonstrate the consistency without much restrictions on the data frequency, and the in-field asymptotics framework, we will show the stable convergence for the proposed estimators. In this talk, I will focus on the second moments of noise. So if the readers are interested in the estimation of the arbitrary moments of noise, please read the paper. And in principle, we can estimate arbitrary phantom moments of noise in this general framework. As I said earlier, our result are based on the framework in Jacod and Zheng, where the efficient price is an Eaton semi-martingale satisfying certain regularity, standard regularity conditions and assumptions. This is a broader class of stochastic process which allows for stochastic volatility and jumps. And for the observation scheme, we allow for random observation times. And as a consequence, the total number of observations upon time t, upon a fixed time t, is random. And the spacing between successive observations is also random. The random spacing is related to the regular spacing as follows. We have two additional non-negative semi-martingales. Roughly speaking, the alpha, the first semi-martingale alpha, or the inverse of alpha, captures the conditional of the random spacing relative to the regular spacing. And the alpha bar, the second process, alpha bar, captures the reflects the conditional variance of the random spacing relative to the regular spacing. For the noise, it takes a multiplicative form. We have another non-negative semi-martingale gamma, which represents the scale process of microstructure noise. Therefore, it can capture the intraday pattern of microstructure noise. There is a second component, the chi. This stationary sequence is centered at 0 with unit variance. So this characterizes the serial dependence of microstructure noise. We allow for very general dependence patterns. In particular, the covariance could decay at a polynomial rate, and the serial dependence, the degree of serial dependence, is captured by this little way here. Finally, the observed price becomes the sum of the efficient price and the microstructure noise. Now we introduce the new estimator. So for any non-negative integer L, we want to estimate the L's order or the covariance of noise. And the new estimator is as follows. You can observe the basic element in this new estimator takes the form of the product of two increments over a pair of disjoint intervals. Here is from I minus 2kn to I, and here is from I plus L to I plus L plus kn. So it's two non-overlapping intervals. Therefore, we call this regime the realized moments of disjoint increments, which has a very nice abbreviation, ReMeDI. So why does the ReMeDI approach work? Recall that the observed price has two components: the efficient price plus the microstructure noise. So for the time being, we can consider this gamma process as constant to illustrate the intuition behind this approach. So the ReMeDI part of the efficient price is relatively small, is asymptotically negligible if the bandwidth Kn is relatively smaller compared with the number of observations. So, but for the ReMeDI part of the noise here, after we expand the product, those last three terms that will disappear because Kn is very large and the two terms are roughly independent. So what remains is the moments of the two leading terms, which is basically the object of interest. So here we have the theorem for the consistency. The ReMeDI estimators of the L's order of the covariance converge to its probability limit, which has two components, so corresponding to the multiplicative form of the noise. So the first part is the average scale of noise upon time t, because we allow time varying noise. And the second part, this RL is actually the autocorrelation, the L's order autocorrelation of the microstructure noise. Recall that the chi part, the stationary part, has unit variance. Therefore, this is essentially the autocorrelation of noise. So, and more regularity conditions, we can derive a stable convergence in law for the proposed estimators, where we have a bit complicated standard asymptotic variance. So it can be further decomposed into another two components. The first part is essentially the core of this asymptotic variance. It has two components as well, corresponding to the multiplicative form of noise. So this is a variance introduced by the time scale of microstructure noise, and this little s here is the variance contributed by the stationary part of noise. So the blue part here, the second part of asymptotic variance actually is induced by the random observation scheme. So if in a regular sampling, sampling scheme, the alpha bar will be identically 0. So this term will drop out. In the paper, we provide consistent estimators of the asymptotic variance. Therefore, we can construct confidence intervals to evaluate the accuracy of the estimators. A surprising yet very intuitive property of the ReMeDI approach is that it also works in beyond the in-field framework. So in particular in those classic time series, the long span time series setting, this non-in-field long span setting, we still achieve consistency. So the intuition is that consider this ReMeDI part of the efficient price. So it consists of the product of martingale differences, but over non-overlapping intervals. Therefore, by the martingale property, it has expectation 0, and it will disappear in the limit. And the ReMeDI part of the noise is still identified with the parameters of the noise that we actually want to estimate. And even a CLT is also available in this non-in-field setting. Therefore, this property broadens the applications of the ReMeDI approach. In particular, it can be applied on low frequency data. For example, when we can apply the ReMeDI approach to decompose daily returns or even the quarterly GDP growth rate, etc. Now let me compare with the benchmark work, the local averaging estimators. So the paper by Jacod and Zheng made several significant contributions to the high frequency literature. Specifically, they provide a very general framework to study color noise with a random stochastic sampling scheme. And they also provide, the consistent estimators of the moments of color noise. So this LA method is based on the deviation from local averages, and while the ReMeDI approach is essentially a differencing method. So both methods are widely used in econometrics. The LA method is asymptotic and more efficient, although we can also improve the efficiency of the ReMeDI approach by, for example, combining different bandwidths, but this is not pursued in this current project. The ReMeDI approach performs better in finite samples in the sense that it's quite robust to noise to signal ratios and to sampling frequencies, and also to the choice of tuning parameters. In terms of computational efficiency, this LA approach, the ReMeDI approach is also faster than the LA methods. And what's more importantly, the ReMeDI approach also works in the non-in-field setting. So it has wider applications to, for example, to asset pricing and even macro time series analysis. So now, next, I'm going to implement the two methods on two data sets where the noise to signal ratio are very different. So in the first sample, the two estimators generate very similar estimates. In particular, they see, well, the time that the microstructure noise in this stock tends to be positive correlated, and the other correlation drops to 0 after, for example, 15 lags. But in the second sample, where the noise to signal ratio becomes smaller, there are differences between estimators. In fact, one can verify that this discrepancy is induced by final sample bias of the local averaging estimators. But the ReMeDI approach remains to be relatively more robust, to the model specification and to the underlying properties of the underlying processes. We consider this is an advantage in real application. Then I think that's pretty much I want to say. But in the paper, I should take the opportunity to mark the paper. And in the paper, we have more results. And if you are interested in this ReMeDI approach, so please read the paper. Thank you.
Okay, thank you very much, Merrick. Okay, let me check the Q&A. So nothing right now, but if people have a question, they can raise their hand. While they're thinking about it, let me ask one simple question on the previous slide. I think it was the previous slide. What is the corresponding autocorrelation here? This is just a curiosity question. But like what's the maximum persistence according to these two estimators?
Well, well, seems like an AR1 process, but this autocorrelation cut cut 0 after lag, I think 7 or 8, and then 8 will cross the horizontal line and then revert to 0 after many lags. So I think we have microstructure models to explain the various parts of this autocorrelation function. For example, for here, this positive autocorrelation is more likely to be caused by the continuous trading of high frequency orders, and the negative autocorrelation, also not quite significant, is more like the inventory control by the market makers. So
my question was a little different from that. It's even simpler than that. It's simply what's the y-axis when you convert it to correlation rather than covariance? Have you looked at that?
Yes, we do have, but it's not included in the slides. But it's decaying like an AR1 process, obviously.
Yeah, I'm just curious about the first order autocorrelation.
The first order autocorrelation.
The number. But it's okay. I mean, obviously, if you don't have it off the top of your head, that's.
I think it's like 0.4, 0.5, something like that.
Yeah. Okay. All right. So quite high. The other thing I wanted to get your opinion on was when I look at this slide here, it looks to me like evidence that the local averaging approach has a bias term in it. Like it flattens down. It looks like it's just shifted up by 0.5 times 10 to the minus 8. Yeah. That's kind of consistent with your simulations in the paper? Is that your interpretation as well?
Yeah. I mean, this financial bias, it takes the form of fraction of the integral volatility. So in fact, we try to to correct the bias, in the simulation, and then we find, well, after the bias correction, the two curves fit very well.
Yeah. Okay. I see. Okay, well, I think people must be fatigued. So let me thank you for the presentation there.
Thank you.
And if you would mind not unsharing your screen. Okay. then I will finish today by saying, first of all, thank you to our speakers for their presentations. I really appreciate you guys being here today. And I know this is an unusual job market season, and I hope today gives you a little bump in publicity for your job hunt. And let me give you an advertisement for the next SoFiE Seminar. The next SoFiE Seminar will go back to our usual format. Our speaker will be Patrick Gagliardini from the University of Lugano, and his discussant will be Seth Pruitt from Arizona State University. That's in 2 weeks' time on October 19. So thank you again, everybody, for your presentations today, and hope to see you in a couple of weeks' time.